Welcome to my channel. In the previous video, I explained merge-sort algorithm for sorting the elements. In this video, I am going to explain the time complexity of merge sort. But before going to see the time complexity of merge sort, once again I will give overview. So, what is merge sort? Generally, we can solve merge sort by using divide and conquer approach. So, according to divide and conquer approach, we are going to divide the problem into sub-problems. And if those sub-problems are relatively larger, again we are going to apply divide and conquer approach for dividing the problem into sub-problems and so on. So according to merge sort, we divided the problem into two sub-problems of equal size. If still those two sub-problems are relatively larger, again we are going to apply divide and conquer approach, means merge sort, for dividing the problem into two sub-problems of equal size. So every time the criteria for dividing is dividing the entire problem at mid. Again, if problem is relatively larger, again we are calculating mid and we are dividing problem into two equal parts at mid again, so on. So we continued this particular approach until getting the smallest sub problems. So smallest means in element related problems, smallest sub problem means if the problem is containing only one element, then we treat them as smallest sub problems. Okay. So based on that, generally there we applied the conditions. There one set of statements are there for true case and another set of statements are there for false case. So for constructing time complexity or for calculating time complexity of such type of problems, generally we need to construct one recurrent relation. First, I am going to write the general divide and conquer approach time complexity representation, and by using that representation, we can make use of that and we can convert it into the recurrent relation of merge sort time complexity. First, I will write the general divide and conquer approach time complexity. Suppose if any problem is containing n number of elements, then we can write a time complexity representation as, suppose if n is small, R1, if n is small, generally we get time complexity directly. That means we can solve directly the problem, and from that by using z of n, we get the time complexity. Or otherwise, we are dividing problem into some sub problems, k sub problem. Let us use k sub problems. K should be greater than or equal to 1. Suppose if problem is p, then we are going to divide the problem into p1, p2, so on, pk sub problems. Okay, na? This problem has its own size. P2 has its own size. Like that, I can write a T of N1 plus T of N2 plus dot so on T of Nk. Where N1 is the number of elements in P1, N2 is number of elements in P2, so on, Nk is number of elements in Pk. Okay, na? So the meaning of T of N1 is the total time needed for solving N1 element problem and the total time needed for solving N2 element problem and so on. Is it clear now? So if you collect all the time complexes individually among all these elements, all the problems, if we add these two time complexes, we get total time needed to solve n element problem. And we can rewrite, because every time we are converting the problem or we are dividing problem into some sub problems and so on. Okay, na? Suppose if n equal to 1, then the total time needed for solving the problem is T of 1. Because this is smallest. N element problem is smallest, there we cannot divide further. Is it clear now? Suppose if n is greater than 1, generally we are dividing problem into sub-problems. Assuming that we are dividing problem into a number of sub-problems and each sub-problem is containing n by b number of elements, then we can write the recurrent relation from the above expression is T of 1 is, if one element problem is there, then for solving one element problem we require T of 1 time, and if you apply divide and otherwise, if n is not equal to 1 means some elements are there or more than one element is there, in that case we are applying divide and conquer approach and we are going to divide the problem into sub problems. So like that we express the expression. Suppose if your problem is dividing a number of sub problems and each sub problem is containing n by b number of elements, then the total time needed to solve n by b number of elements like that a number of sub problems plus this f of n is, here we are applying divide and conquer approach, then f of n is for dividing and combining. Some time is required. So dividing purpose some time is required, combining purpose some time is required. The total time is represented as f of n. So this is the general divide and conquer approach related recurrent relation, time complexity recurrent relation. Now I am making use of this particular expression. I can rewrite this particular expression for merge sort like this. What is merge sort? Generally, merge sort is dividing the problem exactly into two equal halves. Means At mid, we are going to divide the problem into two subproblems. Again, if these two subproblems are relatively larger, again we are applying the same constraint, same criteria, means mid sort. And again, this subproblem is divided into two equal halves. Again, this problem is divided into two equal halves, like that. Okay, so I can rewrite time complex like this: T of 1 or constant. You can write it as constant, A, B, or any constant if n equal to 1. If n equal to 1. Okay, n equal to 1. Otherwise, if n is greater than 1, we write 2t n by 2 plus n. Because if n equal to 1 means the problem is very smallest. Then for solving that particular smallest problem, some constant time is required. Either you take a, c, or any variable, any smallest number, any smallest character or lowercase character, that is used for representing constant time required to solve one element problem. Or otherwise, we can write 2t n by 2 plus n. N is f of n. We are replacing f of n with n or 2n. As you wish, you can, because dividing purpose we need some time, and combining purpose we need some time. So if you combine these two timings, generally we get either 2n, 3n or some constant in n. No need to worry about constant. Then directly take n. Okay. So what do you mean by 2t n by 2? According to merge sort, we are dividing n element problem into two n by 2 element problems. Okay, na? So if you calculate time needed for solving one n by 2 element problem, if you multiply one n by 2 element problem with 2, we get the total time needed to solve an element problem. Okay. Then now I am going to show how this particular recurrent relation can be expanded. So generally I have already explained. So generally, if recurrent expression is there, if it is unknown, by using substitution method we can solve this, or we call it a repetitive substitution method. So by using repetitive substitution method, we can solve T of n equal to 2t n by 2 plus n. I will show you now how we can solve this this particular expression using repetitive substitution method. Okay, this is unknown term in previous relation, because if n equal to 1, there is a constant time complexity that is required to solve the problem. If n is greater than 1, then only this expression is required. There I already told that some constant into n, because for combining purpose, if n elements are there, for dividing purpose n units or n minus 1 operations are required. For combining purpose, one more n minus 1 operations are required. Combinedly we treat it as some 2n or 3n. That's why I am taking Cn here. C is constant, some constant as a coefficient. So this total time is the combining time, dividing time and combining time. This is the solution time. For solving n by 2 element problems, this is the time required to solve one n by 2 element problem. T of n by 2 means, like the two T of n by 2 element problems are there. First solve one n by 2 element problem and multiply this n by 2 element problem with 2, then we get total time needed to solve n element problem. And this is carry anyway, because this is division time as well as combining time. So that's why I put coefficient as constant now. Okay. So if T of n is 2t n by 2 plus Cn, then okay, we write T of n by 2, because we need to solve this. Anyway, 2 is carry. 2 is there as coefficient of T of n by 2. Now we need to rewrite based on T of n equal to T n by 2 plus Cn. You are supposed to write T of n by 2 expansion. How can we write T of n by 2? If n is there, we got T of n by 2. If n by 2 is there, we get 2t n by 4. Because one n by 2 element problem can be divided into two n by 4 element problems. Like that, n by 4 element problems, like that, we get two element problems. If n is there, we got Cn. If n by 2 is there, we get Cn by 2. Anyway, this Cn we need to take here. Because if you see the division, if initially n element problem is there, if you apply divide and conquer approach, this n element problem can be divided into two equal halves, n by 2. That is happened here. Now this each n by 2 element problem is divided into n by 4. So one n by 2 element problem can be divided into two n by 4 element problem. Like that, two n by 2 element problems are there. Okay, na? N by 4, like this we get. Okay, na? Initially there are 2 power 0 number of problems are there, one problem. And if you apply one divide and conquer approach one time, we get 2 n by 2 element problems. If you apply divide and conquer approach 2 times, we get 4 n by 4 element problems. If you apply one more time, then we get n by 8 problem. This n by 4 element problem can be divided into 2 n by 8 problems. Again, this problem is divided into 2 n by 8. Like that, how many problems we get? 8 n by 8 means 2 cube. Okay. So every time, if you apply divide and conquer approach, we get problems in exponential manner. Problems are growing in exponential manner. Okay, na? So like this we get. Suppose 2 into 2, 4t n by 4 plus 2 into cn by 2, cn plus cn, 2cn. If you apply divide and conquer approach one time, we get two sub-problems. Each sub-problem size is n by 2 elements. If you apply divide and conquer approach one more time on these two n by 2 element problems, we get 4 n by 4 element problems. 4 n by 4 element problems. If you apply divide and conquer approach once again on these 4 problems with n by 4 element each, then we get 8 n by 8 problems. Again apply one more time. After that we generalize. Okay na? Now expand one n by 4 problem. Take 4 as common and solve this problem. How we get one n by 4 element problem can be divided into 2 n by 8 problems. 2 n by 8 element problems plus cn by 4 plus 2cn. Anyway, 2cn is there. This 2cn writes here. Then we are going to expand this. Okay, so one T of n by 4 problem, one n by 4 element problem can be divided into 2 n by 8 problems. 2 n by 8 problems. Okay, na? So first we need to calculate 1 n by 8 problem related time and multiply it with 2. Then we get 1 n by 4 element problem and multiply this total time by 4. We get total time needed to solve n element problem. Is it clear now? So if you expand it, 80 n by 8 plus 4 into cn by 4, 1 cn. Already 2 cn is there outside. Then 3 cn. Okay. If you apply divide and conquer approach one time on an element problem, we get 2 n by 2 element problems. Once again, if you apply divide and conquer approach on these two sub problems of size n by 2, then we get 4 sub problems of n by 4. If you apply divide and conquer approach one more time on 4 n by 4 element problems, we get 8 n by 8 element problems and cn. If you write it in through 2 power format, 2 3 t of n by 2 power 3 plus 3 cn. If you apply divide and conquer approach 3 times, we get 2 power 3. Here also remainder as 2 power 3. Then we get coefficient for cn as 3. Okay na? So we need to apply this divide and conquer approach required number of times. Required number of times means we need to apply this divide and conquer approach on each and every sub problem until reaching one particular status. At that particular status, we cannot apply divide and conquer approach further. Means if that particular sub problem cannot be divisible further, then we can stop there. Assume that particular application is k or I. If we apply I times, if you apply one time, we got 2 sub problems. If you apply 2 times, we got 4 sub problems. If you apply 3 times, we get 8 sub problems. Means every time, based on number of applications, we get number of problems as 2 power number of applications. 2 power. If you apply divide and conquer approach 2 times, we get 2 power 2 number of sub problems. If you apply divide and conquer approach 3 times, we get 2 power 3 number of sub problems. If you apply divide and conquer approach I times, we get 2 power I number of sub problems. Here there is no possibility of division. There is no possibility of division means this must be equal to n, because here we are dealing with element problem. If you deal with element problem, assume that array is containing n number of elements. Then if sub problem is containing only one element, we cannot divide it. So if you reach that particular status, n equal 2 power I. If you apply I times divide and conquer approach, obviously we get 2 power I number of sub problems. So as we have already seen here. Suppose if that particular 2 power I is equal to n, means at this particular stage we cannot divide problem into sub problems further. Is it clear now? Because that is simplest. If problem is containing in single element, if all the sub problems are containing single elements, we cannot divide it further. Then take it generalized one. So 2 power I t of n by 2 power I. If power I is there, then we get ICN. Is it clear now? Is it clear up to this? Because if you apply one time, we get 2 sub problems. If you apply divide and conquer approach 2 times, we get 4 sub problems of n by 4 elements each. If you apply 3 times, we get 8 sub problems of n by 8 elements each. Okay na? So like that, if you apply I times, then we get 2 power I number of sub problems, and each sub problem is containing n power 2 n by 2 power I. Because 3 times if you apply, we get remainder as 2 power 3. So n by 2 power 3 number of elements are there in each sub problem. If you apply I times, then remainder becomes 2 power I. That means n by 2 power I number of elements are there in 2 power I number of problems. So each problem is containing n by 2 power I number of elements. Like that, we got 2 power I number of sub problems. So there is no further division means we assume that each problem is containing one element. Each sub problem is containing one element. So like that, we got n number of sub problems. So if each problem is containing one element, we cannot divide it further. Then this is the final expression. This is the final expression. Then we are going to simplify this expression now. We are going to simplify this expression now. Okay, after applying divide and conquer approach on merge sort I times, we got smallest subproblems. So finally, we got this relationship 2 power I t of n by 2 power I plus ICN. Okay, na? So after applying I times, we got 2 power I number of subproblems that is equal to n because we got smallest subproblems. So element related problems, the smallest subproblem means if each subproblem is containing one element, then we cannot divide it further. We cannot divide it further. So that's why we stopped here because we got the final stage now. We got final stage now. Now simplification is required here. Okay, simplification is required. What is 2 power I? 2 power I is equal to 1 n because if you apply one time we got two subproblems. If you apply divide and conquer approach 2 times we got 2 power 2 problems. If you apply divide and conquer approach 3 times we got 2 power 3 problems of size n by 8. Okay, if you apply I times we get 2 power I number of subproblems. We decided that if you apply I times we got only smallest subproblems. So what do you mean by smallest subproblem? If problem is containing one element, we get one element. We say that that problem is smallest subproblem. So like that we got n number of smallest subproblems. N number of smallest subproblems. Then simply replace 2 power I with n. T of n by 2 power I means 2 power I equal to n. Replace n with 2 power I or 2 power I with n, whatever it may be. But what is I? If 2 power I equal to n, if 2 power I equal to n, then I becomes log n base 2. I becomes log n base 2. Okay, na? Then simply replace I with log n base 2. So log n base 2 Cn. Then bring this Cn this side. So n into n by n means T of 1 plus Cn log n base 2. Cn log n base 2. This is the simplified one. What is T of 1? If n equal to 1, I have already told if n equal to 1, some constant type is required. Already I used A, then use A. Okay, na? If n equal to 1, then T of 1 time is required for solving one element problem. Then T of 1 is obviously constant. Then replace T of 1 with A, then An plus Cn log n base 2. That is T of n. Okay, like this we got expression. This is expression. If you substitute, but we are going to represent this particular time complex in any representation, either big O, omega, or theta notation. Okay, na? So what is big O? Worst case time complexity. What is big omega? That is best case time complexity. What is theta? That is average case time complexity. But if you see the merge sort is very blind procedure. A rigid procedure. We call it as rigid procedure. Rigid means blind procedure. Okay, na? Blind procedure. Even you take sorted array. It doesn't worry about whether you give sorted array, unsorted array or semi-sorted array. It blindly, suppose if you give 2, 4, 6, 8, 10 for sorting, merge sort blindly divides this into 2 equal halves. Again this problem into 2 equal halves. Again this problem into 2 equal halves like this. Even you give some sorted elements and some unsorted element like this. The blind procedure, what I told, base sort is blind procedure. Which automatically divides whatever the array you give. Either you give sorted array, either you give semi-sorted array, either if you give unsorted array, blindly merge sort divides array into 2 equal halves, and again that particular 2 sub-arrays are divided into 2 equal halves, means 2 equal sized sub-problems and so on until reaching smallest sub-problems. After that it start merging the elements I have already explained in merge sort. Okay, so if you give sorted array, if you give unsorted array, if you give some sorted elements and unsorted elements related combination, which blindly processes the elements by dividing the entire array into 2 parts at mid, again which considers 2 subproblems. If these 2 subproblems are relatively larger, again merge sort divides this problem into 2 subproblems and 2 subproblems until reaching the smallest subproblems. Okay, so that's why even if you give best case input, even if you worst case means unordered input, even if you average case inputs means some sorted elements and some unsorted elements, we get the same time complexity. So that's why merge sort is requiring best case, average case and worst case time complexity is same. I am going to show what is that particular time complexity. See here. Now this is the expression. So how can we represent the time complexity in terms of big O, omega, theta? If expression is available, now start substituting n value here. Start substituting n value. Substitute n equal to 1, substitute n equal to 2, substitute n equal to 3 and so on. Where suppose this is highest order term. Generally we treat it as order of z of n because compared to n log n base 2 is greater. Compared to n log n base 2 is greater. So while representing this entire term in terms of time complexity using either big O, omega or theta, we need to select or we need to consider or identify so which term is greater. Either this term is greater or this term is greater. Anyway, we are going to omit C and A because these two are constants. A is constant, coefficient of n, and C is coefficient of this entire term. Anyway, we are omitting A and C, and we are concentrating on n here and n log n base 2 here. N and n log n base 2 here. Then we need to decide which one is greater. Either n is greater number value or n log n produces greater value. So obviously, n log n is greater. Okay, then we can represent time complexity as order of n log n base 2. Okay, na? So T of n equal to order of n log n base 2 is the time complexity of merge sort. But this time complexity is the same in best case, average case, and worst case because we have already seen even if you sorted array as input means best case input. Even if you semi-sorted array means some elements in order, some elements in not in order. This is average. Worst means all the elements are not in order. In three cases, merge sort blindly proceeds, dividing problem into subproblems. Again, dividing that subproblems into subproblems until reaching smallest subproblems. There the merge starts. There merge sorts. That's why. So this is the time complexity under merge sort for three cases. Best case order of n log n, average case order of n log n, worst case is also order of n log n. Is it clear now? So that's why the time complexity of merge sort in three cases is order of n log n. Then we can derive this particular time complexity in this way. Okay, na? So after getting generalized one, after this we need to substitute or simplify 2 power I t of n by 2 power I plus I cn by using this expression. And we get order of n log n is the time complexity. Okay, time complexity. In the next video, I am going to explain the next sorting technique, that is quick sort. And I can also explain by taking one example, and I'll explain the time complexity for quick sort. Okay. Thank you for watching my video. Thank you so much.